Okay, so before we start the talk, I just want to give a brief introduction to Tina. Tina Eliassi is a professor of computer science at Northeastern University in Boston and a core faculty member at Northeastern's Network Science Institute. Prior to joining Northeastern, she was an associate professor of computer science at Rutgers University, and before that, she was a member of technical staff and principal investigator at Lawrence Livermore National Laboratory. Tina's research is at the intersection of data mining, machine learning, and network science, and her work has been applied to personalized search on the World Wide Web, statistical indices of large-scale scientific simulation data, fraud detection, ethics in machine learning, and many others. Her algorithms have been incorporated into systems used by the government and industry, as well as open source softwares. Tina has more than 100 peer-reviewed papers, some of which have received Best Paper Awards or Runner-Up Best Paper Awards, and she has served as the program co-chair for prominent data mining, network science, and computational science, social science conferences like KDD, NetSci, and IC2S2. She has received an Outstanding Mentor Award from the Office of Science at the US Department of Energy in 2010. She became a fellow of the ISI Foundation in Turin, Italy in 2019. And she was named one of the 100 Brilliant Women in AI Ethics in 2021. She joined the inaugural external faculty at Vermont Complex Systems Center in 2021. Today, we are pleased to have Tina at the Data Science Initiative at Brown, and she is going to tell us about her work on geometric and topological graph analysis for machine learning applications. This work has been published at Journal of Complex Networks and the Journal of Applied Network Sciences. So I just pass the stage to Tina.
Thank you. Thank you so much, Shahzad, for the invitation, and thank you all for being here. So as it was mentioned, I'm going to be talking about geometric and topological graph analysis, and this work is funded by National Science Foundation and the Army Research Lab. These are the two papers. The papers are published in network science venues because after I left Rutgers and joined Northeastern's Network Science Institute, my students are mostly network scientists, and so we publish in that venue. When in Rome, you publish in venues of Romans. And the collaborators are Pablo Suarez Serrato and Kevin Chan, and this work is all the mastermind of my brilliant student Leo Torres, who's finishing in August and is joining MPI for Mathematics and Sciences to work with Jürgen Jost in Leipzig. So when Leo started about 5 years ago, he came to my office and said, what concepts and procedures can we take from geometry and topology and apply them to mining and learning from complex networks? Leo's background is in applied mathematics. And so we decided to look at two problems. The first one being graph distances. So you have two graphs, for example, two chemical compounds, or two email graphs or two social networks, and you want to see how far they are. And of course, distances and similarities play a key role in many algorithms in machine learning. For example, when you're trying to cluster data points, here the data points, for example, could be graphs, you need some measure of distance. And then the other one is embeddings. I'm not quite sure if we can get to the embeddings, but I'll highlight it at the end. So what we wanted to do is, can we come up with a principled way of deciding distances between graphs? And as you can imagine, measuring similarity is ill-defined, and hence the flip side, measuring distances, is not very well-defined in general. So for the first part, in terms of graph distances, I'm going to tell you about this thing called the length spectrum. Then we're going to take a slight detour into the non-backtracking matrix. Usually when you think about graphs, you think about adjacency matrices or Laplacian matrices, but people oftentimes don't talk about the non-backtracking matrix. So we're going to show some love to the non-backtracking matrix. And then I'm going to introduce our distance measure, which is the non-backtracking distance, followed by what are some of the properties of this distance function, and then some examples. And since this is Zoom and one can doze off easily, I'm going to give you the spoiler alert up front, and then I'm going to fill in the holes. So the first one is, in terms of mathematics, what we found is that the length spectrum of an unweighted graph characterizes its two-core uniquely up to isomorphism. So if you get a graph and you shave its dangling edges, you're going to get its two-core. And at this point, you should think, oh my gosh, this length spectrum thing should be an infinite mathematical construct. And how are you going to actually have an algorithm that could compute it? And that's actually what we spent a lot of our time on. Then in terms of networks and network science, I'm going to show you how the eigenvalues of the non-backtracking matrix track some important descriptors of graphs, such as degree distribution and triangles. So when you think about especially social networks, the two processes that dominate social networks are the fact that you have a heterogeneous degree distribution because of preferential attachment, and closing of triangles. That is, wedges that close because friends of friends are also friends. And then in terms of machine learning, I'm going to show you how the eigenvalues of the non-backtracking matrix are a great way of measuring distance. So that's the spoiler. So let's first start with the length spectrum. So we were inspired by this paper that Constantine and Lafont wrote in 2018. The preprint of it was out when Leo started. It just took a couple of years for the paper to actually come out. Where they showed that there are sufficient conditions for the isometry of two one-dimensional metric spaces, and that isometry induces isomorphism. And I'm going to go through this in detail next. But this is the link to the paper. Their paper came out in the Journal of Topology and Analysis. So the main theorem of Constantine and Lafont, simplified, is as follows. They define the marked length spectrum of a one-dimensional metric space X as a function L that assigns to each homotopy class. So the way to think about a homotopy class is like a geometric region in this metric space, the length of the corresponding minimal geodesic. And they define the convex set to be the union of all the geodesic closed paths in this X, which is the metric space. And then their theorem showed that if an isomorphism preserves the marked length spectra between two metric spaces, X1 and X2, then their convex sets are equal, approximately equal, and that isometry induces isomorphism up to a particular base point. And I'll talk about the base point as we go along. So I'm not a topologist or an applied mathematician. This is how Leo explained it to me, that I feel like I understand. But the question is, how does this apply to graphs at all? Well, we can think about graphs as, or a particular graph as a metric space. Nodes are the elements, and then you have a distance function between the nodes in that metric space. And a natural way of defining a homotopy group for a graph is to look at every geodesic closed path, and that is the non-backtracking cycle. That is, I can go from I to J, but not immediately back to I. And then the convex set for this G will be the two core of the graph. And so the equivalent version of the theorem that Constantine and Lafont showed for graphs would be that if an isomorphism preserves lengths of non-backtracking cycles, then the two cores of two graphs are isometric, and that isometry induces isomorphism up to the particular base point. And here I'm just showing you a picture of a graph where you shave its dangling edges and you get its two core. And so from this, and the paper talks at length about how we derive this, that the length spectrum of a graph characterizes its two core. Again, I'm dealing with topology, so I need to have cycles. I can't deal with tree-like shapes. So the length spectrum of a graph characterizes its two core uniquely up to isomorphism. So now I still haven't told you how I'm going to actually compute this length spectrum. So how do I actually construct this length spectrum? So given a graph where I have the nodes V and I have the edges E, I'm going to pick a node, any node, and I'm going to call that the base point. I talked about the base point a few times. So now this V, which is red, is my base point. And what I'm going to do is I'm going to consider the set of all walks that start and end at V. So here, this could be a walk that is instantiated in this graph where I start at V, I go down and I trace this triangle and then I go back up. Okay, I can do this also for every node, but for now, my base point is this node V, and I'm finding the set of all closed walks that start and end at V. Then what I'm going to do is I'm going to define equivalent classes. So these equivalence classes are going to be walks that only differ by their tree-like parts that don't go through the base point. So if you look at, for example, this equivalence class, this closed walk is exactly like this one, except that the one on the top doesn't have the this dangling edge. I think you can see my my mouse now. I don't know if you were seeing it before. You were. Okay, and so I pick my base point. I find the set of all closed walks, and then I group them into these equivalence classes based on this definition of equivalence, which is they only differ by their tree-like parts. Like here, these two only differ by this dangling edge, which is a tree-like part. So
May I ask a question?
Yes.
Can you go back one slide?
Yeah. This one or the other one?
This one. The thing you've labeled equivalence class, the bottom graph there. You can't actually take a path that goes out along that dangling edge because it has to come back from there. So that would be an IJI thing, wouldn't it?
Yeah, but I haven't talked about the non-backtracking yet.
Okay, so you're looking at the entire loop space. Got it. Thank you.
Yeah. Excellent question. Thank you for paying attention. Excellent. So now I have my equivalence classes. So now what I'm going to do is I'm going to come up with what's called the set of representatives, which is the fundamental group. These are all terminology from homotopy. I pick my base point. I find the set of all closed walks. I group them into these equivalence classes. And then from each equivalence class, I pick the shortest closed walk. And I then will put them all into this group that I'm calling the fundamental group. Now, one of the issues here is that as a graph miner, I don't want to go through different base points. I don't want to have to then say, oh, this is my V, and I have to find all the sets of closed walks. So what I'm going to do is what computer scientists are really good at, which is bastardizing things. So I'm going to say closed walks are equivalent if they differ by their tree-like parts, and not that they differ by their tree-like parts that don't go through the base point. So I'm basically getting rid of the base point idea. And then I'm going to now also, since I got rid of all those dangling edges, at this point, what is remaining in the representative set is just going to be the non-backtracking cycles of G. And so then the length spectrum assigns to each closed walk the length of its shaved version. So if I have something like this, then the L of this will be 3, the L of this will be 3, the L of this will be 3. So what I have now, and the L of this will be 3. So what I have now is, okay, if I can find the set of all non-backtracking cycles in the 2 core of a graph, then that would be its length spectrum, and then I can measure distances between the 2 graphs. So then the question becomes, how do I do this? One is, how do I actually find the set of all non-backtracking cycles of a graph, which is a hard thing. You can ask Matteo. And then the second thing is, how do I actually compute the distances between the length spectrum? So one of the things that we're going to do is we're going to examine outputs instead of inputs, and we're going to partition the set of outputs. So what do I mean by this? If you give me 2 graphs, I don't actually have to enumerate over all the non-backtracking cycles. All I care about, all the length spectrum cares about, is the count. So all I care about is actually finding a histogram of the different counts of non-backtracking cycles in the 2 graphs. So here, for example, for G, it's the number of triangles that I see in G, right? So number of non-backtracking cycles of length 3, number of non-backtracking cycles of length 4, 5, 6, 7, so on and so forth. And then if I have this histogram, then this represents the length spectrum of the two graphs, and then I can compare them. I can compare then the histograms. So this is where we're going to take a slight detour to the non-backtracking matrix, because we're going to use the non-backtracking matrix to find these histograms. So what is the non-backtracking matrix? It doesn't get enough love from either the graph mining people or the network science people because it's a very big graph. So if I have a graph G with vertices V, edges E, where the number of edges is M, the non-backtracking matrix is a 2M by 2M matrix, where for each directionality of the edge, I have a row, and for each directionality of the edge, I also have a column. So here, for example, I can go in this graph from red to blue and blue to yellow. So I have a 1 here. I am not going from a red to blue and blue to red again. This is not allowed for Boton. So I'm going to have a 0, right? And I have another one, red to blue, blue to green. I'm going to have a 1. So this is my non-backtracking matrix. It's only going to have a 1 if I have this basically a 2-hop path where it doesn't have an immediate backtrack. And this is actually the unnormalized version of a random walker's transition matrix that can't immediately backtrack. So it's similar to an adjacency matrix on the set of the directed edges. Now, one of the things that you will see is that if I take this matrix B and I multiply it by itself k times, or take b to the power of k, what I'm going to get is the number of non-backtracking walks of length k. In particular, if I take b and I take it to the power of k, and then I look at the edge E1, and where that intersects with the edge E2, I'm going to get the number of non-backtracking walks of length k that start at E1 and end at E2.
So I have a question here.
Yeah.
So you fix this direction of edges and that gives you the non-backtracking matrix because the direction...
So the non-backtracking matrix, in fact, has encoded in it that I'm not going to look at the things that are going the reverse way, right? By its definition, I'm going to put it 0. I'm going to say this is not allowed.
But your matrix, your graph is not directed, right?
Yeah, but any graph that is not directed, I can make it bidirectional, right? And then just say you can't immediately go back to yourself.
Yeah, but my question is, these directions are like, how do you choose these directions for your matrix?
So we're dealing with undirected and unweighted graphs first. So that's one assumption, right? And I said this is a 2M by 2M matrix, right? So I will have a representation in this graph for both directions. It's just going to be very sparse. But that's fine if it's sparse, right? The issue, like part of why graph mining people don't like non-backtracking matrix is that if M is on the order of n log n, where every node has on average log n neighbors, right? You don't want to have a matrix that big, right?
Yeah, I see.
Okay, so this is where we were. So then if I take B to the power of k, and I only look at the diagonal entries, and I sum the entries in the diagonal, then I'm going to get the number of non-backtracking cycles of length k. Because I'm only looking at the diagonal, so EI and EI. Now, since I'm summing the entries in the diagonal of a matrix, that's just the trace of that matrix B to the power of k, which is telling me the number of non-backtracking cycles of length k. And if you remember what trace is, that's just the eigenvalues of this non-backtracking matrix. So now I have been able to transform this to, just take the eigenvalues of this B matrix. And we'll get to some of the properties of these eigenvalues. For example, you're going to have both real and imaginary parts for B. But in terms of graph distances, then all I needed was this number of non-backtracking cycles of a certain length. I'm going to generate these histograms, and then I'm going to compare the different histograms. So then the non-backtracking distance of the two graphs, G and H, are going to be the cumulative density functions of the respective spectral densities for graph G and graph H. And then I can use something like the Earth mover distance to measure how far these density functions are to each other. Now, the one thing is I don't want to find all the eigenvalues of this non-backtracking matrix B. And so in the paper, we talked about how a good choice for how many to look at are the number of eigenvalues whose magnitude is greater than square root of lambda 1, lambda 1 here being the largest in magnitude eigenvalue of the non-backtracking matrix. So it's a good way, it's a good heuristic for picking a value for this hyperparameter R. So then really computing the non-backtracking distance is really easy, and you can download the code here, and at the end I can share my slides with you. You give me two graphs, you can give me the number of eigenvalues that I need to compute, or I can set it by using this heuristic. And what I will do is I will shave your two graphs down to their two core. I'm going to compute the non-backtracking matrix for the shaved graphs. I'm going to find the eigenvalues up to R, and then I'm going to measure the Earth mover distance between them. Now, the one trick in terms of, or not trick, but one issue here is how are you going to actually put this non-backtracking matrix together? And the runtime complexity for that is m, which was number of edges, plus n, which is number of nodes, times the second moment of the degree distribution. Now, if you give me your graph in like an adjacency list format, then it will take a little bit less time to put the non-backtracking matrix together, but this is what it is. So now, what are some of the properties of this non-backtracking distance? As I said earlier, the National Science Foundation gave us money to actually look at graph distances that are metrics. Unfortunately, our measure is not a metric. It is not because it doesn't satisfy the triangle inequality. It's because of the identity of indiscernibles. That is, you can have two graphs that have identical spectra, but the graphs are different. And in fact, this is what's called co-spectrality. And co-spectrality actually can happen both in terms of the adjacency matrix, the Laplacian matrix, and the non-backtracking matrix, where you will have graphs that are actually different, but they will have the same eigenvalues. And here, this picture by Leo shows you the smallest co-spectral graphs with respect to the non-backtracking matrix. And co-spectrality is where there's still a lot of work that can be done. So it was shown that almost all trees are co-spectral. There is an open problem in terms of how many graphs are co-spectral. And there's a conjecture that as your graphs get bigger, the chance of them finding their co-spectral twin goes down. That is, it's difficult to find, let's say, a graph the size of the Facebook social network that will have a co-spectral twin. So we're relying on that look for your graphs. You're not going to meet a co-spectral twin. So then, what are the properties of the eigenvalues of B, the non-backtracking matrix? So one of the things is hubs, right? When you think about graphs, you think of preferential attachment, you think of hubs. Here I'm showing you the configuration model with parallel degree distribution. This is 10,000 nodes, average degree being 10. And so I'm showing you in terms of as we reduce the number of hubs, what happens to the real and imaginary part of the spectrum of B. And what you're seeing here is that as hubs get fewer and fewer, you lose your imaginary part, which is actually kind of interesting because hubs are kind of like unicorn, right? Like you have these stars that everybody wants to connect to. So as you reduce your hubs, your imaginary parts of the spectra go away. Others have also observed this phenomenon. And then in terms of triangles, which are the other interesting concept in graphs, especially social graphs, is as we increase the number of triangles, and here I'm showing you the spectra for a de Shreni graph, you lose the nice values that you had around the origin. So we're still studying this in terms of what is going on. We know that others have also observed this. So in terms of data sets, so how does this thing actually perform? We looked at both synthetic and real graphs. These are Barabarshi-Albert, configuration model, Erdős-Rényi, hyperbolic, Kronecker, and Watteau-Grass, different number of nodes, so on and so forth. And then we also looked at a bunch of different data sets from online social media, online social networks, mostly like Facebook, etc., to co-authorship networks. So we separate co-authorship networks from, for example, a Facebook social network, because co-authorship networks are projected bipartite networks, and they actually have very different properties. For example, they have a lot more connected components, peer-to-peer file sharing, and autonomous systems. So just the first thing in terms of just sanity check is that as you change a graph, you would expect that the distances will grow. So here on the x-axis, you're seeing percentage of the edges rewired, and then the distance from the original graph. So here, for example, the HEP-TH co-authorship network is as I increase the percentage of the edges rewired. So here, when I get like 100%, I'm basically having a random connection between the original papers. We see that the distances are going up. And then the other thing that we did was look at clustering. So here you're looking at the real and imaginary eigenvalues of a whole bunch of synthetic graphs. Every dot is an eigenvalue. I'm showing you 200 eigenvalues, and it's 50 graphs per model. So I take the Barabarshi-Albert graph, random graph model. I generate 50 graphs from it. Then for each graph, I find a non-backtracking matrix, and then the top 200 eigenvalues of that, and I'm showing you what it looks like. And some of the things which is interesting is that we're not seeing any random graph model that has eigenvalues that lie, for example, here or here or here or here, which is interesting by itself. And then what we did was we took this data and we fed it to UMAP, so Uniform Manifold Approximation and Projection, to see how the clusterings come out. And one of the things that we see here, so you're seeing the x-axis being the first component after you do the dimensionality reduction, the projection with UMAP, and the second component. And every dot here is a graph, and we see a nice separation between the different types of random graphs. Some of the mistakes that this approach makes is between Barabarshi-Albert, Kronecker, and configuration model, and those are actually very close to each other. So we don't fault the algorithm for it, the accuracy of it in terms of separating synthetic graphs that we know which process generated them is up in the 90s. We also looked at heat maps in terms of distances. So here for each of the matrices, the heat maps you're seeing, the diagonal is dark navy, which is distance of 0. Obviously, the distance of one graph to itself should be 0. Some of the things which are interesting here is that the social graphs, so like the Facebook graph, a Twitter graph, etc., they're actually fairly close to each other, and they are different than co-authorship networks. And some co-authorship networks are very different than other co-authorship networks. And one of the reasons here is different disciplines actually operate differently. Obviously, like in the way co-authorship happens in computer science is not the same way as it happens, let's say, in biology or in philosophy. which co-authorships are actually very rare. And then this is for the real networks in terms of peer-to-peer networks that are very similar to each other, and then autonomous systems. And then this is in terms of the random graph models that we have. We also tried it in terms of spectral clustering and seeing how well we do in terms of grouping the different graphs. Here, so this is the mandatory shot for a data mining or machine learning paper where you compare your approach to other approaches and you say my approach is winning. So we have the non-backtracking distance where I automatically pick the number of eigenvalues. Then there is the non-backtracking distance where I say just find the top 300 eigenvalues. In the paper, we extensively talk about the number of eigenvalues across different scenarios, different data sets, different random graph generation. We also compare it to CDG. This is the graphlet correlation distance where you're finding graphlets and then you're measuring the correlation between their occurrences. We looked at the top 300 eigenvalues of the Laplacian matrix, since everybody loves the Laplacian matrix. We also compared it to ESCAPE. This is where this is a paper that Ali Pinar et al. Had at the World Wide Web conference, where you're finding motifs and you're counting those motifs. And then lastly, we also looked at an approach that was published in Nature Communications, where you're looking at the distribution of the shortest path lengths between each pair of nodes. And we picked these, obviously this is not exhaustive, like everybody and their mother has a graph distance or a network similarity measure. We only picked the ones where they're looking at some structure in the graph. So we're looking at non-backtracking cycles, they're looking at graphlets or motifs, so on and so forth. And then what I'm showing you here, you can think of this as basically precision and recall. So completeness is you can think of it as recall, and homogeneity as precision. And these gray dashed lines are what's called the V measure, which is similar to the F1 score. And so we are this blue box, and you're seeing that I'm not showing ESCAPE on this plot because ESCAPE was actually below 0.5. And again, this is where we're saying, okay, our model, at least for now, or our distance, at least for now, is better than the rest of these people. And then, so in terms of summary, just to bring it around, I talked about how it's good to actually put together the non-backtracking matrix, find its eigenvalues. There are good ways in terms of tracking the degree distribution and the triangle distribution. And it's a great way of measuring distances. And then behind you, like one of the reasons that we feel it's good in terms of measuring distances, because it links back to the theorem that Constantine and Lafont showed, because it's related to the length spectra, even though we bastardized it. So you can find the paper there and the code as well. And I'm happy to answer some questions here for about 5 minutes before I go on to embeddings for this first part. I saw there was 2 questions in the chat. No, it's not that it's providing. So the one thing is, excellent question, Michael. So does it provide a solution to the graph isomorphism problem? So what does Constantine and Lafont say? They're saying that if an isomorphism exists and you have these marked length spectra that will produce the same value, then that will give you an isometry, and that isometry will then induce an isomorphism for the given base point, right? And so that's a lot already. And like, if you just think about, I have to find like all the non-backtracking cycles in a graph. So not just the simple ones, simple and complex. I mean, that is crazy. So we're just saying like what we're doing makes sense because there are these people who show that actually trying to measure non-backtracking cycles in a graph and using it as distances is a good thing. Okay. And so, because otherwise, like, why should I use your distance measure than somebody else's? And that's what we're saying. Other questions on this one?
I have a question. When you look at these non-backtracking cycles, you're not looking at simple cycles. So there's an infinite number of them, right?
Yeah, and the way we're just getting around it is this analysis that I showed, where it's just like, okay, here's a non-backtracking matrix. If I multiply it up to the power of k, and I take the sum of its diagonals, it's going to give me all the non-backtracking cycles of length k.
Right.
That's just a trace of it. So all I need to do is find the eigenvalues of this matrix, and I'm going to move on.
So you fix k.
So actually, we don't. Yes, yes, indeed. In fact, for us, it's just k is 1. We just
K is what?
K is 1. We just find the the eigenvalues of the non-backtracking matrix, and then we measure the CDF of it. So this is really the
K
pseudocode.
is 1.
Yeah, this is just the pseudocode. This thing exactly that you see is the pseudocode, which is like, I'm finding the top R eigenvalues of the non-backtracking matrix. That's all I do.
Okay.
Right. So, and again, the whole thing about like the length spectrum and the discussion of the length spectrum was just like, look, these topologists say it's a good thing to find non-backtracking cycles, right? And oh, look, I can find non-backtracking cycles, their count, which is what the topologists say I should find, by putting the non-backtracking matrix together and finding its eigenvalues. And I don't even need to find all of it. I only need to find the top R. And I'm doing well in terms of separating graphs that are being generated by different processes. I'm doing well on real world networks in terms of measuring distances between them. Like, I'm not making a huge, big claim. It's just like, oh, look, those guys said the non-backtracking cycles are good.
And I guess just one other quick question. What would happen if you don't put this non-backtracking constraint, if you were just looking at cycles? I mean, yeah, not simple cycles, just you would reduce the complexity of everything, it seems. And I just wonder if you would get anything out of it, or if it's just too weak a measure.
I don't know. We didn't try it, because even if I want to find simple cycles,
not simple cycles, just cycles, just remove the non-backtracking.
Yeah. So the question is like, what would be, so I would just work on the adjacency matrix then, right? So in fact, so we didn't look at that. I'm sorry, we didn't look at that. Okay. We actually are going the other way, which is like, what if I say that you have to go 2 hops before, like 3 hops before you can come back, to be able to distinguish between graphs more. So we're actually going higher order now in the work that we're doing. But you're asking a good question. We didn't do that, to just look at, don't restrict the non-backtracking.
Okay, thanks.
Yeah.
So I have a follow-up question.
Yeah.
Is it because you are looking at the eigenvalues, is it that k is 1 or k goes to infinity? Because it seems like you are raising this matrix to powers, and then at the end you are looking at the eigenvalues. So it should be some.
So if I'm finding the trace of b to the power of k, right, then that would be the eigenvalues of b to the power of k.
Yeah, I see.
Right.
So it's not even a backtracking walk, it's just one edge in this graph.
So no, but okay, so let me go back again, right? So I have this non-backtracking matrix representation of the graph, right, that we talked about. And then I'm telling you, look, if I take b and if I multiply it k times, and if I look at an entry in that b to the power of k, I'm going to get the number of non-backtracking walks of length k. And like, you've probably seen this with adjacency matrices, right? Where people multiply them. Like if I get a times a, right, a squared, I'm going to get the number of paths of length 2 in this graph, right? So then I'm like, oh, but all I care about is that you start and end at the same place, because I'm interested in cycles, right? Topology is only interested in poles, as I understand it, right? So then I'm only going to look at the diagonal entries. So if I'm only looking at the diagonal entries and summing the diagonal entries, my linear algebra book says that's the trace of the graph, right? Which then I can find of this matrix, which I can find by finding its eigenvalues. So And then what we're doing is, well, I'm saying, okay, just find the non-backtracking matrix and find its eigenvalues. So we're not, so I'm not doing this, take B, multiply it 3 times, and then by itself take its trace or takes its eigenvalue, and that will give you the number of triangles, right? That's not what I'm doing, right? What I'm doing is, this is basically just an eigenvalue problem of the non-backtracking matrix. So I'm going to take the non-backtracking matrix, I'm going to find its eigenvalues, and then I'm going to just measure distances between the eigenvalues of 2 non-backtracking matrices.
So there's another question on the chat.
You only need the eigenvalues to calculate the trace more efficiently. Yeah. And in fact, here's the thing: if I didn't use the spectra of the eigenvalues, so if like one of you smart people can come up with ways that could give me the counts for the non-backtracking cycles in a graph, then I wouldn't have the co-spectrality problem. And so then, right, I would have a distance measure that perhaps would be a metric as opposed to a pseudometric. So the issue that I have with this being a pseudometric is exactly because I'm finding the spectra of the non-backtracking matrix. But and I'm doing that because of this argument I'm laying out, which is the spectra of the non-backtracking matrix is giving me these counts for the non-backtracking cycles. But if, for example, you can find it with sampling, I know Matteo has done a lot of work. If you can find it with sampling, then perhaps I can satisfy all the measures, all the requirements to be a metric.
So I have another question. It may be just unrelated. So have you thought of like using different values for K? Because it seems like, for example, if you set value of K equal to 3, you are preserving triangles. Like if 2 graphs are like the distance of 2 graphs is 0, it seems like they have the same number of triangles in them. If you set the value of K to 4, it seems like you're either counting like, I don't know, like length 2 cycles or length 4 cycles. So
yeah, we didn't do that. But I mean, the point is that the key, in fact, it was in the chat, Christopher Wolfram mentioned it. As long as I can find the eigenvalues efficiently, both the real and imaginary parts, right, the spectra of it, then of course I can do what you're suggesting, right? Because now I'm multiplying scalars 10 times, 20 times, right? And that wouldn't be that difficult.
Yeah.
So basically, actually, the 2 main computational bottlenecks, just to go back, is how do you actually put the B matrix? Because normally nobody's giving your graph in the non-backtracking matrix representation. We can try to make it popular, and then finding the eigenvalues. Now again, all you need to do is find the counts for the non-backtracking cycle. So if there's another way to find it, then beautiful.
So there is one last question, and then maybe we can continue to the rest of the
Yeah, I'm confused with the spectrum of B gives you information about cycles without raising B to a power. So what we're saying is the B matrix is just good enough if I just find its eigenvalues, because we're seeing good results from it. And I don't need to multiply it by K and add another hyperparameter to it. You may disagree with that, and we could have tried. In fact, that's what Shahrzad was asking me. But really, if the key is the eigenvalues of the non-backtracking matrix, then why should I like multiply them by their power? If I have the eigenvalues, I have the eigenvalues, right? So Christopher Wolfram is saying, I think number of cycles with length K equal trace B to the power of K equals sum of lambda to the power of K. And so if you know the lambdas, you can compute the trace without actually raising B to a lot. Yeah, exactly. Thank you.
So let's just move on and take more questions maybe offline, because
thank you, Christopher. Okay, and then the last thing, and I know we have only an hour, I'll go quickly through it. You can read the paper. Is about embeddings. Everybody and their mother is doing embeddings these days. Embeddings is I have a graph and I want to map the nodes into some vector space. That would be node embedding. There are people who are doing edge embedding. There are people who are doing the entire graph embedding. And the idea is that if I do this embedding into this lower dimensional space, I will have better features for my data to then later do machine learning on it, whether node classification, link prediction, community discovery, et cetera, et cetera. And so one of the things that Leo did was that what we want to do is we want to do node embedding based on the geometric properties of the spectral decomposition of the Laplacian matrix. He came up with this method called GLE, geometric Laplacian eigenmap embedding. And the spoilers here are from the mathematics side. We know that there's a bijection between an undirected graph of n nodes and the n-1 dimensional simplex. In terms of networks, we can encode the graph structure in geometric terms using the simplex geometry of the Laplacian. And in terms of machine learning, what we found is that for the very popular graph embedding methods that exist, such as node2vec, which was produced at Yuri Leskovich's lab, what they do is they only look at distance minimization. That is, if two nodes are close in the graph space, then they should be close in this embedding space. And because they're only looking at distance minimization and not geometry, they don't do well if you're looking at a graph like peer-to-peer, like a protein-protein interaction network that doesn't have a lot of triangles. So most of the popular graph embedding methods only look at graph distance minimization, and they perform well when your clustering coefficient is high. And so when you look at the geometry, you could say, oh, do I lie on the same manifold with this other node, and so on and so forth. So it's not just about distance minimization. And so that work came out in this Journal of Complex Networks. You can see the details there. And at least from the network science perspective, there's been a lot of recent interest in terms of using topology, using ideas from topological data analysis to do graph mining. And so that was basically what we were piggybacking on. So that's it, really. I'm happy to answer any other questions that you may have. Thank you.
Thanks to you. So if there, I guess we had a lot of questions in the between the two parts, but if there are any other questions, we can discuss
Or
them.
I can give you some open problems to look at.
Yeah, that would be actually great.
So one of the things from the network science side, which is very interesting, is the representation of the graph. So whether it's a simple graph, whether you're representing it in terms of a simplicial complex, where you want to look at more than just dyad, where you want to capture the fact that I have a paper with you and you have a paper with Matteo, and then I also have a paper with Matteo, that you cannot capture if it's just dyadic, or whether I want to represent it as a hypergraph. And of course, as I move up to the hypergraph representation, where I don't know what the spectra of the hypergraph exactly means, at least for like simple graphs representation, like an adjacency matrix. I know what lambda1 of the adjacency matrix means for a simple graph, right? It's path capacity. And for example, the eigenvectors of the non-backtracking matrix, the first eigenvector and the second eigenvector of the non-backtracking matrix give me edge centrality, and they also give me the modularity that is in the graph. But when I go to hypergraphs, I don't know what the spectra of a hypergraph actually mean. So you have a representation issue. How should I represent this phenomena? Hypergraphs, simplicial complexes, simple graphs. depending on the choice that you make, you may find, for example, different anomalies. If you were to measure something as simple as clustering coefficient, which is like the number of triangles that you have over the total possible triangles that you could have, you'll get different values. And so this was actually in SIAM News. So Austin Benson and Des Chaim and others just recently in January had an article in SIAM News. We have an article that's coming out in SIAM Review about the different choices. And then there was another article that was just published in Physics Reports by Baptistian about these different choices, because the network science community at least is moving more toward higher order network structures, move beyond dyad, right? Like I want to know that when Matteo sends me an email, I always forward it to Shahrzad, or most of the times I forward it to Shahrzad. And so looking at that level and above and beyond just, oh, like Tina sent something to Shahrzad. So that's one of the things. Which representation is the best one for your data? The old problem of representation.
So do you think that like this problem, a specific distance that we can use could be like choosing a subset of these eigenvalues, like how many of like you said, you choose the square root of the largest one for some of your experiments, like why that? Like, do you think if you choose the first and second one, like the multiplication of the first and second one, that would give you some other, that would be like?
Yeah, so actually that's a really interesting question. So a couple of things on that. So when you take a class on machine learning or data mining and they teach you, let's say PCA or something, right? They're like, oh, the largest eigenvalue is here, the second one is here, the third one is here, right? There's a sharp drop. And like in social networks, we haven't observed that. Like in social networks, the eigenvalues are really close, like up to like 25 or something. They're extremely close to each other. And so, for example, if you're making modifications to the graph and tracking just the largest eigenvalue, that largest eigenvalue can flip. Here, and in the paper we discuss it more, the reason the number of eigenvalues whose magnitude is larger than square root of lambda 1 is a good one is because that basically captures the majority of the information. So if you think about like in terms of the number of bits that you need to store the entire eigenvalues, that's basically the majority of it. So, and there are actually good, we cited in the paper in terms of good references for that.
Thank you.
Yeah.
So if there are...
Can I ask you another question?
Yes, of course.
It's very silly, maybe. So your matrix is O of the number of nodes to the fourth, right? Because it's the number of edges square, essentially. And then you have to take the eigenvalue of that, the eigenvalues of that. You know, I tell my students in data mining that n to the square is too large and it's too slow. So they should go to, you know, linear and sublinear time algorithms. So
Right.
how can we do that faster?
Yeah, we didn't think about how to do it faster. I'm leaving that to others like you. But yeah, like if you look at it, we're not looking at graphs that are very, very big, right? It's only like 82,000 nodes. We're not looking at it big. But this goes back to what Christopher was saying. Like if there's a faster way of finding the eigenvalues, I would be the user.
I'm thinking, you know, what you said before, maybe if we sample up to length, I don't know, 6. If you can sample the crosswalk up to length 6, maybe this already gives us a good approximation or something like that. Like, do you think that if we
maybe
can sample,
so? Yeah. So the thing with that is that, like, if you think about again the eigen, in fact, in the paper we talk about edge embedding based on the non-backtracking matrix for the first paper that I talked about, with the graph distances. So the first and the second eigenvector of the non-backtracking matrix measure edge centrality and modularity. So then I'm thinking, okay, if I'm only taking the top 2 eigenvalues of the B matrix, in a way, I'm just comparing graphs based on edge centrality and and modularity. I don't know what the third eigenvector of the matrix B means. In fact, that's one of my pet peeves. Like, I would love to understand like what the eigenvalues or eigenvectors of these matrices actually mean. Like, as I said, like the largest eigenvalue of the adjacency matrix, we know it has to do with path capacity. In fact, that's why when people want to stop pandemics, they want to drop the lambda 1 as much as possible. So cut edges or nodes that drops the lambda 1 of the adjacency matrix as much as possible. So that's great, right? But like, what does the third eigenvalue of the adjacency matrix mean? Who knows?
Oh, thanks.
Yeah, good question though. Yeah, if you can come up with a faster algorithm to finding eigenvalues, call me. Call me. Don't text, just call. Go ahead, Shahza.
Right, this reminds me of a paper that we just like went through. So this thing that you are saying that the first eigenvalue is like path capacity in your word and mixing time in my terminology. I think there is a paper that talks about like how the average of a function over a Markov chain is approaching its mean value. And there they talk about like how some of these eigenvalues are orthogonal to this function, and then they don't matter at the convergence rate of this function towards its mean. And I think that's kind of like answering the kind of question you're asking, like to estimate the empirical mean of a function, like different eigenvalues of a matrix of the Markov chain can be playing different roles. That's what the paper is discussing.
Yeah. Yeah. Oh, great. I would love to have that reference. That would be great, because it's probably it's related to this thing that you're talking about. Right?
Yeah, I will definitely share that. Like, we found that also recently, and I think it's a very interesting paper, and nobody didn't get enough attention.
I see.
Yeah. Okay, so thank you very much for the very interesting talk. I guess we are just running a little bit out of time. So this talk will be recorded and we will put it online in the Data Science Initiative website. So let's thank Tina again, and yeah, thanks for all the audience.
Thank you. Thank you. Thank you very much, Sharzad, and thank you all for joining and for your excellent questions. I hope you found it interesting.
Yeah, it was very interesting.
Take care, everyone.
Thank you.
Bye-bye.